So let's do this example that shows something about both the notion of velocity and displacement, and also shows something about right and left endpoints. So what I've done is I've given a chart that indicates what the velocity of a particle is at particular times. In other words, we don't really know what the velocity of the particle is at every time. For example, we don't know what it is at time t equals 1, but we do know what it is at t equals 0, 2, 4, 6, 8, and 10. In other words, at all the even numbers. And of course, we don't know what it is at any of the fractional times. So all I know is that whatever this function looks like, it hits the red points that you see in this graph here, where of course this is going to be time in minutes, and on the vertical we have velocity in meters per minute. I've simply chosen those as the arbitrary units. I could have used miles per hour, could have used centimeters per second, I could have used light years per century. Any units of distance and time will work. So what we want to do is using n equals 5, in other words, using 5 rectangles, we want to find the approximate a, the displacement, and b, the total distance traveled. So for the displacement, we're going to use left endpoints, and for the total distance traveled, we're going to use right endpoints. Again, there's nothing about total distance traveled that makes right endpoints a better approximation. I'm just trying to mix up the examples a little bit. So first of all, recall that from some previous comments that displacement is the area is the signed area under the velocity function. Go back a minute. When I say signed area, what I mean is that we treat areas that are above the x-axis as positive, we treat areas that are below the x-axis as negative. So that's what I mean by signed area. We're going to add up these blue areas and subtract the purple area. So going back to this example, you can see that there are some points that are below the x-axis and some that are above it. When I use left endpoints, here's what it's going to look like. What we're going to do is we're going to treat the function as if it encloses this area here, because for the first interval, I'm using the left endpoint of the interval. The first interval, since I'm taking the total interval going from 0 up to 10 and dividing it into fifths, we know that because I'm choosing 5 subintervals, that means each one is going to have a length of 2, and I'm using the left endpoint of each interval to stand in for the height of the function at that point. So for that interval rather. So for the next subinterval, which is going to be 2 to 4, we're going to have this rectangle. Again, I'm choosing the left endpoint of the subinterval. Go to the subinterval 4 to 6, and I'm choosing the right endpoint, which looks like that. Then I've got 6 to 8, 8 to 10. There we go. So you can see we've got some positive and some negative. And just to understand, we don't know what this function does inside, say, the interval 0 to 2. We don't know how much time it really spends above the x-axis and how much time it dips below the x-axis. So we're simply using a rule, the rule being use the left endpoint to stand in for whatever it is we don't know about that function's behavior. That's why this drawing makes sense. So with that said, what we can see is that the total signed area, which is going to be equal to the displacement, is, let's say the displacement is going to be equal to the area of the first rectangle, so that's 2 times 10, and then plus 2 times negative 4, that's the height, really the height below the x-axis of the second rectangle, plus 2 times 8, plus 2 times negative 9, plus 2 times negative 7. Notice, by the way, that because the widths of these rectangles is always the same, I can simply take the width and put it out here. I can just call this the width, and then I can simply add up the height. So that's going to be 10 minus 4 plus 8 minus 9 minus 7. When we add all that up, we get 2 times 10 minus 4 is 6, and 8 is 14, minus 9 is 5, and then minus 7 is negative 2. So we discover that we have a displacement of negative 4. So the answer to this question is negative 4 meters. Displacement is, of course, a distance, so we answer it in the unit of distance. Okay, so that's part A. Now, The next thing we want to do is answer ask what is the total distance traveled, and we want to do that using right endpoints this time. So what's the difference here? The difference, if I can draw this very, try to draw the motion here, is that we have a particle that goes this way, it goes this way, it goes this way, but all of this motion is distance traveled, even if it's not contributing to the ultimate displacement. In the most extreme example, I have a ball that, let's say, it goes up and then it goes down. By the time it's finished with its path, it hasn't moved at all. Its displacement is zero, but clearly the whole time it's been in motion. It was in motion in the positive direction until it got to the top, then it was in motion in the negative direction until it got to the bottom, which means that when we're counting up how much the object moves, we have to count positive motion as positive motion, but we also have to count negative motion as if it were a positive amount of motion. The way we do that is we simply ignore the plus and minus in this velocity chart and just flip everything to positive. So what I've done here is I've rewritten this chart like this, and what you can see is that if I just move this over a bit so that we can put another column in. If I put in, let's say, a speed column, then this becomes 10, 4, 8, 9, 7, and 3. In other words, everything that was negative becomes positive, everything that already was positive just stays the same. And if I put in what that looks like here, that means that this red point that's below the x-axis becomes like that. This red point that's below the x-axis becomes like that. And this last red point below the x-axis, let's see, that's 9 and 7. So that's going to become like that. Okay, so in other words, what we're doing here is instead of adding up these rectangles, some of which are below the x-axis, we're treating everything as positive. So now we're adding that rectangle, that rectangle, that rectangle, that rectangle, and that rectangle. Try to draw these in different directions so that you can see which rectangle is which. So we're adding up all of these rectangles, and having turned all the velocities that were negative into positives, we see that we're only going to get positive distance, because even motion whether if we call positive motion to the right and negative motion to the left, or if we call positive motion up and negative motion down, either way, negative motion is still motion. So that's why we're treating everything as positive when we add this up. So what we can see is that adding up all these rectangles, we're going to get that, total distance is equal to, as you saw, I can simply take the width of the rectangles because they're all the same and just put it outside. That gives us 2 times, I'm going to use I'm using the right endpoints, so I'm going to use 4 plus 8 plus 9 plus 7 plus 3. Recall that with the previous example, I used the left endpoint of each interval, but the way the problem was stated was I want to do it using right endpoints when I'm doing the total distance, just to change up the type of example that we're doing. So this is going to be 2 times 4 and 8 is 12, and 9 is 21, and 7 is 28, and 3 is 31. So that becomes 2 times 31, which is 62 meters. Again, we're talking about a total distance. We answer it in meters. So this is the total distance traveled by the particle. So it's sort of interesting. The particle actually ends up 4 meters behind where it started, but because it switched directions so many times, it actually travels a total of 62 meters to get there. So what's the lesson here, really? The lesson is that displacement is equal to the signed area under the velocity function v of t. Total distance is equal to the area under the absolute value of v of t. In other words, the function that we get when we simply take any known value of the velocity function that's negative and make it positive. I could say the signed area, except that when we're using the absolute value of a function, there's no issue of the sign SIGN because there are no negative values, so I'm just calling it the area under the velocity function.